Hello students, welcome to the second paper of F.Y.B.Sc Mathematics. F.Y.B.Sc Mathematics paper second. The name of your math second paper is Calculus First. Calculus 1. This is your second paper of F.Y.B.Sc Mathematics. So in this whole paper of first semester, we will discuss the 4 chapters. After, in between those 4 chapters, we will start the chapter 1, the real numbers. The real numbers. Chapter first, the real numbers. We are familiar with these real numbers since our childhood, because in 4th or 5th standard we have seen the numbers, natural numbers, integers, rational numbers, irrational numbers, and all those numbers, that is natural numbers, integers, then rational numbers, irrational numbers, all those integers lies inside the real number. So first of all we will recall some sets. So first set is set of natural numbers. Set of natural numbers. The notation of natural numbers, set of natural numbers, is this n, and we know that set starts from 1, 2, and this set is an infinite set. So first set is the set of natural numbers. Now we will discuss the second set. Second set, suppose set of integers. The set of integers. The notation of the set of integers is z. This is the notation of set of integers, and set of integers contains the negative numbers as well as positive numbers and 0, that is minus 3, minus 2, minus 1, 0, 1, 2, 3, and all these numbers are the set of integers. That is, all natural numbers, negative of all natural numbers, and 0 is the set of integers. Suppose the third set is set of rational numbers. Set of rational numbers. Set of rational numbers. The notation of set of rational number is capital Q, and the set of rational numbers is the set. The elements of the rational numbers are the form p by q, that is 2 by 3. So these are the natural numbers, these are integers, and the set of rational numbers is of the form, the elements of the form p by q, such that here this q is a non-zero number. Also, greatest common divisor of p and q is equals to 1. So this is the set of rational numbers. For example, 2 by 3 is a rational number. Suppose 4 by 5 is again a rational number, and all these numbers are, so the numbers of the form p by q are said to be rational number, where q is non-zero and GCD of p and q is equals to 1. This is the set of rational number. And now similarly this set of irrational numbers. Set of irrational numbers. Set of irrational numbers. So the set of irrational number is the complement of rational number, that is, the numbers which are not rational are said to be irrational numbers, and the examples of irrational numbers are e, pi. Then the rational numbers, irrational numbers means the numbers such that this 1 point, suppose 3 or this 1.333 up to so on, that is this 3 doesn't stop, that is the elements, the numbers after this point does not stop anywhere, so those numbers are said to be irrational numbers. Now we will see our real numbers. Real numbers, the union of these two. So here in the first set we have seen the natural numbers, in the second set we have seen the integers. So one thing here is common, that is the natural numbers all are present in the set of integers 1, 2, 3, 4, 5 up to so on. All these natural numbers are present in the integers here 1, 2, 3, 4, and all those integers, sorry, natural numbers are in set of integers. Now here if we write minus 2 as, suppose this is minus 2 number, minus 2 as minus 2 upon 1, we can write any number, that is 1 by 1 is 1, 2 by 1 is 2, 3 by 1 is 3, minus 1 by 1 is again 1, minus 2 by 2 is again 1. So all these integers can be written of the form p by q. All these integers can be written in the form p by q. So all these integers are rational numbers. So set of integers is totally containing rational numbers. So natural number is containing integers and integers is containing natural numbers, and this set of irrational numbers is a different set. The set of real numbers, real number, notation of the real number is this R, and we can say that the union of rationals and irrational, the union of rational and irrational numbers, rational and irrational numbers, rational and irrational numbers is the set of real numbers, or forms the set of real numbers, forms the set of real numbers. So we can generalize these sets in a single diagram or single tree diagram. Here set of real numbers, set of real number contains all these rationals as well as irrationals, q complement, that is a set of irrational number. This is the set of real numbers. Set of real number contains these rationals as well as these irrationals. Now this rational number contains the set of integers, set of integers, set of integers. So there are again, this set of integer contains 0, set of positive integers, set of negative integers. So just write it as, suppose set of positive integers 0 and set of negative integers. Now this positive integers, set of positive integers contains the set of natural numbers. So this natural number is subset of positive integer. This positive 0 as well as negative integer is set of, this set is called integers. Again this positive integer is containing set of integers, integers are also in integers, 0 is in the integers. So again this integer set of integers is totally containing rational numbers, and this rational as well as irrationals, union of rational and irrational is the set of real numbers. Now we will see some algebraic properties of real numbers. Algebraic properties of real numbers. Next topic is the algebraic properties of real numbers. The algebraic properties of R or real numbers. So in these we will see, in this topic we will see the algebraic properties of real numbers. So these algebraic properties are also called as field axioms. Field axioms. Field axiom. So first field axiom is, for any two elements, suppose F is any set, then for the A and B, suppose be the two elements of that F, then suppose A comma B are the elements of set F. So if these two are the elements of the set F, then their addition, that is A plus B, again belongs to that set F, and this property is called, this set F is closed under the operation this plus under addition. F is said to be closed under addition whenever for any AB belongs to that F, A plus B must belongs to this set F. Second property is for any AB belongs to F, A plus B is equals to B plus A. A plus B is equals to B plus A, and this property is called as commutative property. Commutativity with respect to this operation addition. We can apply addition as well as multiplication on this field F, on this set F. So instead of A plus B, we can write A into B. That was there. That will our next property. Now the third property is for any ABC belongs to that set F, A plus B plus C is equals to A plus B plus C, and this property is called associativity. Associativity with respect to addition. Now the fourth property is existence of zero element, that is there exists some zero belongs to set F such that if we add any number with 0, that is A plus 0 or 0 plus A is equals to that number A, there exists some zero element in that set F such that if we add that 0 with any number, then their addition will be our 0. This is called existence of additive identity. Existence of additive identity. Existence of additive identity. This is our fourth property. Now the fifth property is existence of negative number. So the fifth property is for all A belongs to F, there exists minus A again belongs to that set F such that A plus minus A plus minus A is equals to 0. That is there exists some negative number for every A belongs to that set F. There exists negative of that number such that if we add these A and minus A, then we will get this 0 element. This property is called existence of negative number. Existence of negative element. Existence of negative element. This is our fifth property or fifth field axiom. Now the sixth one. This first property is our closure with respect to addition. Similar property we will see with multiplication, that is for any AB belongs to F, A into B belongs to that F. So multiplication of these two numbers is again F. This property is called closure with respect to multiplication, or F is closed. This set F is closed under multiplication. This is the sign of multiplication. Now the seventh property is again similarly the commutative property with respect to multiplication. A into B is equals to B into A. This property is called commutativity with respect to multiplication. Commutativity with respect to multiplication. Now the eighth property is similar property with this property. This was our associativity with respect to addition, and now we will see the eighth property is associativity with respect to multiplication. A dot B dot C is equals to A dot B dot C. This is associative property or associativity with respect to multiplication. Now the ninth property existence of unity. Existence of unity means there exists, as here there exists 0 belongs to F such that if we add this 0 with any element of set F, then their addition is A. Now with respect to multiplication, there exists 1 belongs to F such that if we multiply any A with 1, then their multiplication is that number A itself. Since here if we add any number A with 0, then their addition is A itself, this A itself. So similar for multiplication, there must be, we have to multiply this number A by some number such that their multiplication is equals to that number itself. So we have to multiply that number by 1. A into 1 is equals to A, and this property is called, or this 1 is called unity, existence of unity. Now the 10th property is, for any non-zero A belongs to F, there exists A inverse, existence of inverse. There exists A inverse. Mostly that A inverse will be 1 upon A. Again belongs to that set yes, such that A into A inverse, that is A into A inverse is equals to 1 by A, is equals to 1. This unity. A into that A inverse is equals to that unity. Then this element A inverse is called inverse. So this property is called existence of multiplicative inverse. Existence of inverse or multiplicative inverse. Existence of inverse. And now we will see the last property, which will our distributive law. The 11th property, distributive law. Distributive law, that is, this last law is A into B plus C is equals to A into B plus A into C, AB plus AC. So this is the last property, which is distributive law. So if any set F satisfies these all 11 properties, then we say that set F, or that any set which satisfies these 10 properties, is called field. So the next definition and the most important one is field. The definition of field. Definition of field. This is the definition of field. A non-empty subset, a non-empty set F, which is subset of R. This, in this chapter we will see the all properties of real number. So here F be any subset of R with two binary operations, with two binary operation. Here in the first 5 properties we have seen the operation addition, and the remaining properties, so 6, 7, 8, 9, 10, in the next 5 properties we have seen the operation multiplication, and in the last property, that is in the 11th property, that is the distributive law, we have seen those multiplication as well as addition together. So any non-empty set F with two binary operations, two binary operation, that is two operations, addition and multiplication, with two binary operations. First one is addition, and the second one is multiplication. It's called field. It's called field if it satisfies all the above axioms. If it satisfies the above axioms, that is, if any non-empty subset of R satisfies, if any subset of R satisfies all these 11 properties, then that subset of R is said to be filled. Is subset of R is said to be filled. So after this definition, we will take one note. The set of real numbers itself a field. Also this, if we are seeing the definition of field as any subset F of R. F is subset of R. A subset F of R, a non-empty set F of R is said to be filled if it satisfies the all above the properties. But this F is itself satisfies all these 11 properties. Therefore this R satisfies all the above 11 properties. So this set R is called filled. Similarly, the set of rational number also satisfies all those properties. So we can say that set of rational numbers is also a filled with respect to same addition and multiplication. So we will write one note here. The set of rational numbers, the set of rational numbers and the set of real numbers. The set of rational numbers notation is Q, and the set of real numbers notation of the set of real numbers is R. R fields with respect to addition and multiplication. With respect to addition, usual addition means the addition and multiplication. With respect to usual addition and usual multiplication. So this note gives us a set of rational numbers as well as the set of real numbers forms a field with respect to usual addition and multiplication. Usual addition and usual multiplication means the addition that we generally use, also the multiplication that we generally use. So this was it for our first lecture. So you have to write all these things just like I have written. You have to write all these definitions as well as properties in your notebook. So we will see the remaining topic in next lecture.